Okay, so from today I want to have really a very good lecture rather than talking the side track. And we are going to talk this morning deterministic and random or stochastic. So we are going to get into first the deterministic phenomena. If you know the deterministic phenomena, then if you exclude all such a phenomena, so it's going to be a random. But I'm going to talk to you about the deterministic, which you may know already, like a Fourier series, Fourier integrals, all that. We'll go through that. Then your base is all set. Okay? And for deterministic, of course, one case is periodic phenomena. Another case is, of course, the non-periodic. Even periodic case, as I wrote down here, is simple, the sinusoidal, sine or cosine function, or simply the harmonic functions. And among the periodic, another case is complex periodic, so which I'm going to show you, including periodic, then non-periodic, the phenomena. Then we'll talk briefly about I talk about that in the phenomena, when we look at the phenomena itself. Then after that, we'll get into, of course, the non-periodic, such as almost periodic. What does it mean, almost periodic? It's not fully as sinusoidal. It's not complex periodic, somewhat periodic, but almost periodic. So which I'm going to tell you, then I will assign some problem, not giving you a hard time, just to think a little bit and practice a little bit. So I'll give you homework tomorrow. Then you can really plot that and all that. But I demand you should know at least some tools like a MATLAB tool, MATCAD if you have. There are all different kind of the tool. So you have to use it to plot the functions and all that. And the non-periodic, among the non-periodic, the transient phenomena is also very important. Transient phenomena. So we're going to talk about this. Okay, now random or stochastic phenomena, you can say that. And it's cold. Today it's cold. Yesterday was pretty good in the afternoon. For the stochastic phenomena, one case is stationary phenomena. Another case is the non-stationary phenomena. What does it mean, stationary? So I'm going to really define. This is all the defining process. When you look at the signature, usually time domain signature, then you should be able to classify where this particular signature belongs to. Okay? Then within the stationary, there are two classes of phenomena. One is algorithmic process. Algorithmic phenomena is kind of When you deal with stochastic phenomena, this algorithm, you will use this heavily. Of course, I'll explain to you after I give you a big picture. Another case is a non-algorithm within the stationary process. I just use sometimes process, sometimes phenomena, sometimes stochastic. I call as random. It's all same. But I just use one time this definition, another definition. That's all same. A non-stationary process, you will see that. That's, of course, not the stationary process, and that's very special case problem. Okay? Okay, we'll start from simplest one, which is deterministic. And among the deterministic, we're going to talk about the periodic function. Periodic function, of course, you know the periodic function, which is simple sinusoidal function. And here, of course, F naught is the frequency in cycle per second, plus theta, that's a shift, okay? Theta is angle. So here, we all know this. This is even high school, maybe freshmen would know this. But xt is equal to x sine omega t plus theta. I'm going to deal this sine function as a random function after I discuss about the deterministic functions, okay? So to make this for a random function, what should I do? I want to make this as a random function or stochastic function. Any idea? I can make this guy, simply speaking, random or stochastic. Then this function becomes the random function. It has a variation in time, unpredictable the variation, which does not follow the particular rule. So of course capital X is deterministic. So of course this is X is half of the amplitude. This is peak to peak. You sometimes in the random nature, this is called amplitude, but in vibration this is really called amplitude. That's what the X here. And if I express omega, this is radian per second. If I convert it to a frequency, so naturally omega is equal to 2 pi f. Is equal to 2 pi f. This is radian per second. This is cycle per second. So this is omega. So f, cycle per second, f is equal to 1 over t, right? T is period of one cycle. So if I say this, I gave you already chapter 1 appendix, which is really intro of my vibration class note. So take a look at that few page for appendix. You can tell all that. So here is you can think as this is center point, and this point is small mass, and this is a string. Then if you start to turn this counterclockwise direction, then of course you can think about this way. So this is like omega t. It goes to 90 degree. Then if you plot the projection of motion of this mass, it's gonna go like this. And theta is of course the angle that you can set. You can say preset angle. Then you can think of the angle here, some angle as a theta. Then theta, this is like omega t. You can plot as omega t over t, a lot of different way. Then you can think of, okay, if this guy starts at 90 degree, then this is 90 degree is up here. So you can say, okay, it start the motion of the pendulum or mass from there. So this is very simple relation, but it's very basic, but you can't afford to make mistake in very basic. So this is amplitude. And this is of course a time domain. When you throw this in the frequency domain, okay, so we're going to talk also about frequency domain function and the time domain function. So I plot over there is in frequency. This is a time, okay. Then what I plot there as amplitude here, x. So omega happen to be there, or the frequency. If I to distinguish between just the notation omega or frequency, I'm gonna put the not there. Then I can make it T naught. If you look at my note, I use TP. It's all same thing. And it's right there. So you can say this is just a peak right at the particular frequency. So usually it related to power spectra, cross spectra, all that frequency domain function as we will discuss it. You need a frequency domain function. Without this, it's very difficult to analyze it. Okay, so that you have to be a kind of careful. So if you read a little bit ahead of my lecture, you can read my lecture notes and all that. That's really my lecture note. I spend a lot of hours to generate the lecture note. And if you really listen carefully my lecture and read my lecture note, I think that's about all you need. But once in a while you can go back to see a few reference book, then that you can improve yourself quite a bit. So this is not allegory, this is separate. This is deterministic, and among the deterministic, simply the periodic functions, okay? I keep talking, then I really accumulate and all that. Complex periodic. Complex periodic is somewhat different, but not greatly different. Something like general function. Sinusoidal is really a harmonic type of the function, but let's say it can be simply t, okay, or you can plot with omega t, but let's say this is periodic, but it's a complex periodic. But let's say simplest among them, this is like a periodic. It keeps repeat. So if I write here, the function xt is equal to x t plus minus n. What I used, ntp or t naught, and over here n start to 1, 2, things like that. And here I don't put the 0. If it's a 0, what happens? It converges to the original function. There is no reason to repeat. And not only this, other function is like this is all same interval. This is all same interval. This is TP. This is all TP here. One period. No period. That's not the periodic function. That's not the complex periodic function. So over here, you can have like this, and it repeat the same thing. Identical one is here. It's the same function. Repeat. Okay, so you know what I'm saying. It's just to repeat. Repeat by itself. So you can tell that that's more than harmonic function or simple sine function, which is composed of a few the harmonic function. So for such a periodic function can be expressed using the Fourier series. So Fourier series, you know about the Fourier series. And one of the bad things using the PowerPoint is just use your own eye. That's own eyeball and rolling. And of course you can hear, and you don't write usually, but writing is also very important. You use all the sense. When I prepare, and before I come, I also review, make sure I follow the concept and all that right. So it's a good idea when you go back. You should not memorize. In my class, I don't want you to memorize anything. Please don't memorize. In the exam or homework, if you need anything, I'll give you all the tools, whatever. Memorization is a disaster in engineering. So, but you can just rewrite, make sure you understand, and all that. And the classical Fourier series is this one. Everybody remember? Everybody remember Fourier series? It's a combination of a whole bunch of sine cosine plus a naught over 2 is a DC value, direct current value you call, or that's a mean value. But all the signal analysis combined with the variable signature or dynamic signature, you can always remove the DC value for the convenience. You can because DC, first this is a DC value plus all the dynamic signal. And DC, you can take them outside. And you can add the effect later. So that's what you can do that. So here is half of the A naught plus summation n is equal to 1 through infinity. Did I use n there? Yeah. And general notation, an cosine omega nt plus bn sine omega nt is really classical notation for the Fourier series. Okay, so over here, this is a classical notation. In this classical notation, this is a t. I can say this is omega n. Omega, let me see, I'm not sure whether I should use that right now here. And you can put all the tick mark. And here, this omega n is 2 pi fn. If I just carry over up to the t, this is what sometimes I can use omega nt, sometimes use 2 pi fnt, doesn't make any difference. So that's why I mentioned to you always you have to open your heart all the time, except when you read paper, some people use omega n, some people use fn. Doesn't make any difference, okay? And also this, I can rewrite this guy as a 2 pi n times fn t. Over here, I use fn is equal to n times f1. So f1 is something like a fundamental or first frequency. Okay. Or, so here, I can write over here as n over t1, or this is equal to n over tp, just notation. whether you express fnt n times f1t, or some people use n times f naught t, doesn't make any difference. So what does it saying over here is fn minus fn minus 1. So for this is, let's say, this is fn t. Then I have to change this guy as simply fi. I varies from 1, 2, 3, 4. So now I'm gonna say this guy is fn minus 1t, or this I can write as n times f1. This guy is n minus 1 f1t. So I can say this is interval f f1. I can simply say this interval, just this interval. This is not a very, very good idea. I will simply say delta f. So this guy is like, I carried over t, then you might have to carry over t all the time. Delta f is a constant, right? So every interval is a fixed value of delta f. So this is a typical classical Fourier series, okay? And here, if you integrate this directly with respect to time t, directly you integrate, then if you integrate, then what should I have? I'll do just 1. Then integrate one period from 0 to time. I use tp, but t1, who cares, right? Or t, xt, direct integration by just looking. Without, I just wrote once, but without writing, can you tell the outcome? If I integrate directly like this, okay, what would be this, what would be that, what would be that term? Can you tell? If you integrate directly, so if you integrate directly, Tp A naught over 2 is a constant, right? This guy is a constant. So outcome would be what? What's outcome? A naught over 2 times Tp. That's it. So outcome for this guy is very clear. Outcome is half of Tp A naught, correct? Say yes. Yes. What about this guy? Quick. You're the vibration specialist. What's the integration of one cycle of cosine or sine? Say 0. Right? Say 0. There's no time to think. Cosine. Integration, simply speaking, area in that interval. plus minus 0. So second term, third term is 0. So you can tell right away, saying that, okay, so 2 over Tp here is equal to, I just can directly move this guy. Well, let me rewrite. Tp A naught over 2 is equal to integration for one time interval of xt. So the idea is to find out the A naught. Half of the A naught is equal to Tp. Is it expressed in that? So I can say A naught is equal to 202 Tp xt dt. So you can determine X. Non-quantity over here is the signature xt. Xt can be expressed all this sine cosine function. And this guy's mean value is simply shifting the time domain functions, right? So usually to remove the mean value, you can move this guy to the left-hand side. Then you just determine this, which is dynamic signal. So over here, you have that one. And second term, an and bn, just by looking at how to determine now an and bn, how you do that. You took the Fourier series. There is no question about it. You sometime in the past, somewhere, okay, you took it. But essence is not memorizing. But essence is, what does it do? You have to have determine A and B and all that. That coefficient is related to the amplitude of the sine cosine functions when you throw in the frequency domain. Then you can tell that particular frequency Fn, then how much it contributes for the amplitude. So there is always goals and objective. So it shows here A and Bn happen to be the integration of that guy, integration for that guy. So there is nowadays, if you open mathematical functions and all that stuff, you know, for example, integration of a cosine function is equal to some value. Integration of sine and integration of sine multiplied by cosine function is equal to always, think about it, sine, cosine. Integration of the one period. What happened? I want you to think that integration of sine multiplied by sine function, sine, let's say omega nt multiplied by sine omega mt dt is equal to, the reason I'm telling you by the word is you can think about it right away, what the value would be. This is it's very good homework to practice. So and some are already In chapter 1 appendix, take a look at all the solutions are also there. So we can do that way rather than try to solve all here. So all that very standard math, using the very standard math, I'll just leave it to you, solve in the homework, and I can check it out for you. But at the present time, I'm going to tell you this is an and bn, and to get this expression, you have to multiply by cosine omega mt. One is omega nt here. The other one that you have to multiply is cosine omega mt. So idea is cosine multiplication is not 0. Cosine sine multiplication, when you integrate, this is 0. The next, to get the bn, you multiply all the way through the sine function. Sine function, here cosine sine multiplication, then integrate 0. Okay. So then you can get the expression for bn. Don't say, oh, Professor Shin is not explaining so well. No, it's my intent not to explain too deep. This is stuff you have to know when you multiply, and that's what you need. And another one, as I mentioned to you in the first class, I repeat the same thing over and over again. That way it will stay in your brain for a long time. And this is a classical expression. This is so-called the polar form. In next few pages, also the same thing appears if you read already. A little bit, this is like an appetizer. A little bit saying this is it. Oh, not clear. Then a couple of pages later, if you look at it, very clear. And another approach is complex expression. So three different expression is simply expression for sinusoidal. The Fourier series is required because this is so basic in this class. Before we discuss really random and all that, this is the one we have to know. And over here, so I use this is a frequency domain expression, the amplitude versus the frequency, and this is f1 is 1 times delta f, one interval. This one f2 f1 minus f1 is f1, so that's what that interval. Every interval is the same. But the amplitude related to the given frequency, a contribution to the total frequency is what that is. x1, x2, x3, so on. So this is a classical form, and this is a polar form. And if you look at just blindly look at it, the reason I'm saying blindly look at it, this era has been changed. Believe it or not. in classical approach, when I start to get into the college in early 60s, usually you have to learn this, then learn that, then learn that, then that was the way to acquire the knowledge. But not now. I'm reading Steve Jobs, Job you call. I bought the book yesterday. No, I bought the book on Saturday on the way back from Daegu to Daejeon. I had about an hour in the station, and I happened to find Steve Jobs' book. He is the one to invent the iPhone. He didn't start from learn this, learn that, learn that. No, he just learned basic, then jump to iPhone. So I always talk to KAIST students in the class. Don't try to learn all that. Jump. You have a basic knowledge. Jump to get the iPhone. You can do that. Like myself, I cannot do that because it has a fixed knowledge control my brain. But your case, that doesn't control you. You are in the position to control that. So over here, by just looking at, how can I drive from here down to here? Forget about between. How can you drive this to get that? Vice versa. Can you, with already solutions are here, can you tell that happened to be minus because this is a plus? That's why. Can you, from here, or from here, can you drive from one to the other? By just no writing, just by your head. Can you do that? What you have to do? In class we can talk anything we said, right? We can talk anything. Gusto, what you can do simply. Very simple, isn't it? And as you look at it, x naught here should be same as this, right? That's clear. Mean value is mean value. This guy, how this guy can be that guy, is a cosine. If you expand it, what do you see? I'm not going to write down here. What do you see? If you expand this guy, x, this is xn, okay? Cosine 2 pi n f1t expanded. Next term is what? Cosine? I don't want to really write here. xn. Cosine. Let's use this guy simpler. Summation xn. So if you open this, if you open, this is minus, so it's minus. What do you have here? Cosine plus sine. Correct? Somebody came in? Oh. So if you do that, then what happens? Cosine omega nt, then cosine theta n plus sine omega nt sine theta n. Is this correct? That's all. Sine n. Then I can rewrite this guy as xn. First guy, cosine theta n. Right? Then what's the next one? Next one is cosine omega nt plus what? I have to write this guy. So xn sine theta n put together sine omega nt. You see that now? Getting closer. You can see the picture. You can go through do that. So you don't have to write anything usually. Then sine cosine 90-degree phase difference, you know that. So you can tell from here to there. Then xn, you can tell that theta n divided by up and down together, you can like that. So then you can draw this guy. By drawing this guy, this is simply contribution of the amplitude to the total amplitude. So very straightforward doing that. So you will do you will do all this as your homework. You will wait until tomorrow to get that. So I'll use that's a little bit slow. That's 148. The students are keep peeping because my watch shows 51. What's your watch? What? 50. So I think we should stop at 50. So I want you to train my way to handle the systems, and try to learn by yourself and get the goal a little bit faster. I don't want to hear from you saying, oh, I have to run the computer for 10 hours, then I can tell you what the result is. But for especially for doctoral degree person, you should develop your brain in such a way that you can really trace to the result fast. And that's much better than wait for 100 hours to get the result, computations, and get what's happening. Okay, I'll see you tomorrow at 6 o'clock, right here. Then we'll have a time. You have another commitment right after 7? Tomorrow evening? No. That's okay, we'll see tomorrow. 6 to 7, that's what I'm going to call it. Okay.